Alright, so now on to part 2 where we'll apply what we just reviewed to talk some more about redox reactions. And so on page 540 in your interactive reader, so that's 540, kind of the official definition that we're given for redox reactions is that it's a chemical process where we see elements undergoing a change in their oxidation number. And that's just what we saw with the example of copper with the Statue of Liberty. But now let's go ahead and look at it in another case, and then we'll kind of define some more vocabulary that will be important as we go along. So first off, we're given an equation in word form, so we need to convert it to formulas. So sodium is just Na. Chlorine we know is a diatomic element, so we'll write it as Cl2. And then sodium chloride, this is a synthesis reaction, so sodium has a +1 charge, chlorine has a -1 charge, so as a compound it'll be NaCl. Now, when I go back and balance, I notice that there's 1 sodium on each side, so that's good, but I have 2 chlorines on this side and only 1 on this side, so I'll need to add a coefficient of 2 here to balance that. Then, since that affected how many sodiums I had, I'll then return to the left and add another 2 in front. So now my equation is balanced. Alright, so now let's go through and assign oxidation numbers to each element. So, first of all, sodium and chlorine, they're both just elements that are on their own in their pure state, so they'll both have oxidation numbers of 0. But however, when we look to the right, when they're in the compound, again we'll start to the right, the most electronegative atom. So as an anion, chlorine would have a -1 charge, so that will be its oxidation state. And so sodium, in order to make it neutral, will have an oxidation state of +1. So, if you noticed, sodium here, did its oxidation state change from left to right? It did, didn't it? And the same thing happened for chlorine, where we had a change from left to right. So now what we talked about with oxidation states or oxidation numbers is they're a bookkeeping device for how electrons are distributed. So the more negative the oxidation state, the more electrons that are distributed there. So if we were considering the compound NaCl, that's going to mean that chlorine has the greater share, or in this case it's ionic, has the greater portion of electrons. Okay? And so now let's define some terminology that's specific to redox reactions. So we know that this reaction here is a redox reaction because we do see that change in oxidation number. So now if everyone will look on page 539, we're going to introduce some key terms that'll be helpful to us as we talk about redox reactions. Alright, so the first term we're going to introduce is the term oxidation. And that's when an element experiences an increase in oxidation state. So here, the green line, when we have sodium going from an oxidation state of 0 to +1, that would be the process of oxidation in the case of this reaction. So the way we would phrase that is we would say that sodium is oxidized. Because its oxidation number does increase from 0 to +1. Now, let's talk about what that means when there's an increase. So again, just to emphasize, oxidation states are showing us distribution of electrons. So if the oxidation state is becoming more positive, that means that some electrons have been lost. Okay, so since electrons are negative, if we lose them, that's going to make the oxidation state more positive. So now let's take a look at the flip side, which is reduction. Alright, so in reduction, which will be represented by our yellow line here, an element is going to experience a decrease in oxidation state. So the word reduce, if you think about it, means to decrease, so that might help you make the connection there. So the way we would phrase that in terms of our equation, we would say chlorine is reduced. Okay, chlorine is reduced because what we notice about its oxidation state is that it goes from 0 to -1. Now, if we're thinking about this in terms of electrons, since electrons are negative, if the oxidation state is becoming more negative, then that means that in reduction, electrons are gained. There we go. Electrons are gained. And so what we see is that in a redox reaction, you have both the processes of oxidation and reduction going on at the same time. And that kind of makes sense, because if electrons are being lost, well, they have to go somewhere, and they can't just disappear. And so the electrons that are lost are going to be the same electrons that are gained by whatever chemical species is reduced. So here's kind of a graphic to help illustrate how these processes work together in a redox reaction. So here, if you'll notice, element A is losing electrons, okay? But those electrons are being transferred to compound B. So what we would say is that compound A, since it's losing electrons, that means its oxidation state will be increasing, in other words, becoming more positive. Okay, so that's what's happening to compound A, but as a result, compound B is being reduced because it's gaining that electron, which will therefore decrease its oxidation state or make it more negative. Alright, and here's kind of one more picture to show how that works. So here, element A, again, is losing electrons, but those electrons that are lost are going to element B. So as a result, A is oxidized, meaning its oxidation state increases or becomes more positive, while B is gaining electrons. So its oxidation state is reduced, which means it becomes more negative. Now, the one way to kind of keep track of this is using a handy saying called Leo the Lion says grr. Alright, so there you go. So the Leo part stands for losing electrons is oxidation. Okay, and that's what we saw kind of in this example over here. And then what the GER stands for, it's kind of a funny spelling, but the GER, that stands for the opposite, in that gaining electrons is reduction. So definitely feel free to use that acronym as we're going along to help us keep track of what's called oxidation and what's called reduction. So now let's go on to do an example problem that'll be similar to what you'll be expected to do later on. So here we're given a chemical equation, and the first thing we need to do is to check to see if it's a redox equation. So we know that redox equations have changes in the oxidation numbers of the elements, so we first want to go through and assign oxidation numbers to each element in the compound. Alright, so to save time, I've already done that for you, but if you have any questions, feel free to pause the video and talk with your neighbor to figure out why the oxidation numbers are what they are. So now we want to note how the oxidation numbers have changed. So if I take a look at hydrogen, what I notice is that going from left to right, that's the way we'll read it, left to right, the oxidation number is increasing. Okay, and it's increasing specifically from 0 to +1. But on the flip side, if we look at what's happening to copper, it's decreasing from +2 to 0. There we go. So since the oxidation number of hydrogen is increasing, that's going to be the process of oxidation. I'll just abbreviate it OX for now. And so to kind of remind myself that that was oxidation, I thought back to our saying, Leo says grr. And so when we lose electrons, I know that that'll make the oxidation state more positive. And my acronym kind of reminds me that losing electrons is oxidation. So that's why I labeled kind of our green line, oxidation. And on the flip side, I'm reminded that when we gain electrons, that should decrease the oxidation number. And therefore, that's the process of reduction. And so that's what's happening to copper. So on a test, you might be asked to identify the element that is reduced and identify the element that is oxidized. So taking what we've just talked about, the element that is reduced, in other words, its oxidation state is decreasing. In this case, that's going to be copper. And we'll want to show, how the decrease is happening. So you'll write it's going from +2 to 0. Now on the flip side, the element that's oxidized in this case is hydrogen. And its oxidation state is increasing from 0 to +1. And if we notice, oxygen, it didn't have a change in oxidation number, so it was neither oxidized nor reduced. Now there's one more example I want us to see before we move on to practice. Alright, so in this example, I've gone ahead and written in the oxidation states. But what we'll notice is, do any of the oxidation states change? So in both cases, sulfur is +4 and +4. Oxygen in all the cases is -2 and -2. And hydrogen in all the cases is still +1. So since there's no change in oxidation states, then this is not a redox reaction. Okay, so I just want to go ahead and show you that one case where it wasn't redox since you didn't have a change in oxidation state. So now we're going to move on and actually practice applying what we've just learned.